Hi everybody, today we're going to talk about section 6.3, which is tests for parallelograms. And after this lesson, you will be able to prove that a quadrilateral is a parallelogram and that a set of points forms a parallelogram in a coordinate plane. So let's take a look specifically at some conditions for parallelograms. And in here, the first one, theorem 6.9, says that if both pairs of opposite sides of a quadrilateral are congruent, then we can say that quadrilateral is a parallelogram. Again, you have to be told both pairs of opposite sides. Similarly, theorem 6.10 talks about opposite angles, so both pairs of opposite angles must be congruent. And if that's the case, then we can say it is also a parallelogram. The third one, 6.11, if we have these diagonals and they bisect, we know that if they bisect, then we know that the quadrilateral is a parallelogram. You could also consider that this point where the diagonals meet as a point of intersection, and we're actually going to talk about that later in our examples that we do. And then the last one is if we know that one of the pair of opposite sides is both parallel and congruent, then we can say that that parallelogram is, that quadrilateral is a parallelogram. So let's take a look at some examples. This first one, just as getting at the definition or those theorems that we just looked at, and we need to determine whether each of the quadrilateral is a parallelogram, and we're going to justify our answer. So looking at this first one, I have this parallelogram, and I notice that the horizontal and vertical sides are congruent with each other. And I also notice that the little slanty sides are also congruent with each other. So, because we see that both pairs of opposite sides are congruent, and based on theorem 6.9, this is a parallelogram. Again, we have to be told that both pairs of opposite either sides or angles have to be congruent in order for that to be the case. So with that being said, let's take a look at example 1b. In 1b, we are given that these opposite angles are the same measure, and we are given that these opposite sides are the same length. But here's the thing, we're given one pair of angles and one pair of sides, and none of those theorems that we just looked at are talking about the fact that if you know one pair of angles and one pair of sides, that it's a parallelogram. So we need to say here that we can't prove it, or we can't confirm that it's a parallelogram, because none of the theorems are proven. Theorems are proven. Okay, so again, that's just getting you some exposure to those theorems regarding parallelograms. So let's take a look at example number 2. We need to find the values of x and y so that the quadrilateral is a parallelogram. And thinking back to those theorems that we just looked at, 6.10 tells us that both pairs of opposite angles must be congruent in order for it to be a parallelogram. So if that's the case, and I know that these opposite angles must be congruent, I can set up a problem for each one. That means 56 is congruent to 7x. So I can set up an equation and use what we have talked about in regards to solving equation. And I have figured out that the value of x has to be 8. Okay, and then we can do the same thing for the other two angles, and we can say that 4y plus 4 equals 5y minus 26. And so from here, I'm just going to, again, whoa. Okay, sorry about that. So what we're going to do now is use what all of our skills with solving equations. So I get 4 equals y minus 26. Solving this algebraically. So then I get y is equal to 30. Okay, so let's take a look at our next slide, which is a different concept summary of how to prove that a quadrilateral is a parallelogram. So one of the things that we just talked about, these statements here actually get at the definition in those 4 theorems that we mentioned a couple of slides ago. For me, it just kind of simplifies it. Again, it's both pairs of opposite sides must be parallel, both pairs of opposite sides are congruent, both pairs of opposite angles are congruent. We know that if the diagonals bisect each other, then it's a parallelogram. And then if one pair of opposite sides is parallel and congruent. So just a summary. So one of the things that you can do is take a look at a quadrilateral in a coordinate grid and figure out if it is actually a parallelogram. And so how do we do that? There's 3 methods that you can do. The first one is you can find the slope between points to determine if both pairs of opposite sides are parallel. That goes along with the definition. The second one that you could use is use the distance formula between points. And again, you're looking to see if opposite sides are congruent. Goes with theorem 6.9. And then the last one is that you can use the midpoint formula to see if those diagonals bisect each other. And how do we know if they do that? We know that if they end up having the same point of, if they have a point of intersection where you find that midpoint, then that is considered the fact that they're bisecting each other. And again, that's theorem 6.11. So let's put this to practice. In example 3, we're going to determine whether the quadrilateral is a parallelogram using the distance formula. So we can graph it if we want to. In this case, I'm just going to use the distance formula for each of the 4 sides to look to see if my opposite sides are parallel. Not parallel, excuse me, to see if they're the same distance. So from here, what I'm going to do is, first of all, I'm going to find the length of AB. And again, our distance formula, distance equals, and we're going to subtract the x-coordinates, square them, and add squaring of the difference of the y-coordinates and then solve. So I'm going to look at AB. Again, you can pick whichever one you want to be x1 and x2. In this case, I'm just going to do 3 minus 2 squared plus 3 minus 8 squared. 3 minus 2 is 1. Plus 3 minus 8 is negative 5. And so I square them, I get 1 plus 25. And so I get the square root of 26 as the length of AB. So now I know that side CD is opposite of AB. So what I'm going to do now is do the same thing, except I'm going to use the coordinates of C and D to help us figure this out. So I'm going to do 6 minus 1 squared plus negative 1 minus 0 squared, and do exactly what I just did for AB. So 5 squared plus negative 1 squared. This gives me 25 plus 1, which is the square root of 26. So as we see this, we see that both AB and CD have the same length of square root of 26. Now, if this is going to be a parallelogram, side BC and side DA will have the same measurements as well. So let's take a look. So I'm going to choose to do 8 minus 6 quantity squared plus 2 minus the negative 1 is 2 plus 1 squared, and I'm going to solve, continue to solve. So I've got 2 squared plus 3 squared, which is 4 plus 9, which is the square root of 13. So that's the first one. Side BC is the square root of 13. I'll rewrite that. Okay, so again, if this is going to be a parallelogram, then we hope that side DA is also the square root of 13. Again, you can do this in any order that you want. I'm going to choose to do 3 minus 1 squared plus 3 minus 0 squared, and 3 minus 1 is 2 squared plus 3 squared, which gives me 4 plus 9, which gives me the square root of 13. And lo and behold, just like with A, B, and C, D, we see that these two sides have the same distance or same length. And so we can say that because of theorem 6.9, this is a parallelogram. Okay, so there you have it, properties of parallelograms. Good luck with the rest of your work.